Ready to go? Hey everyone, welcome. So this is the Fundamentals of Engineering. It's going to be Thermodynamics Part 1. I'm going to be doing this again next week to kind of carry on related topic, but related topic to today, but a little bit different. But again, it's all going to kind of be continuing, but the next week is not required to get what you get out of this week. So first of all, I'm going to introduce you to who I am. Talk a bit about my program very briefly. I don't want to spend too much time on it. These slides will be on Blackboard, and I'll give you the link for that. And we have an organization set up for this, so you have access to all of this after the class. So you can read more about it there. But I do want to spend more time on the heat transfer part that we're going to get into after a bit. So first of all, question is, who am I? Well, there you go. That is my pre-COVID fancy beard, and I guess more unruly hair right there. I'm the program director for the Mechanical Engineering Technology program at Old Dominion University. What I do is I focus mostly on thermodynamics, heat transfer, motorsports, fluid, power and energy. My big passion is anything that makes power, whether that's mechanical power to move vehicles, or if it's power that can be converted into electricity to generate the power you need to run your house. So I do most of those types of things. I also do a little bit of fluids. I don't do as much as I used to. One of the main things I do at ODU, aside from being the program director and the chief departmental advisor, we call it, I am the academic advisor for all mechanical engineering technology students. I'm also the academic advisor for ASHRAE, which is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. It says American. It is an international society. A lot of professional societies are international now. I know that started in the U.S. many years ago. I'm not sure when they're going to change the name, but they are an international society. And what they do is any standard and any code. So as an engineer, we have to design things to codes and standards. As a student, you'll probably wonder, where do these numbers come from? How do I know if that value makes sense? Why are you telling me that there's this many cubic feet per minute of airflow into a building? Is that realistic? Well, those numbers all come from engineering codes and standards that were developed by professional societies with the goal of having, here's the standards that we should all abide by. And again, these are not, like scientific standards in terms of how much airflow needs to go into a building. It's based on comfort. So people have said in surveys, they like a certain amount of fresh air in a building. That's where these standards and codes come from. So ASHRAE is anything involving ventilation, heating, cooling, humidity levels, things like that in buildings. A lot of codes. So that's what I do. I'm the advisor for that for the student chapter, and I work with the local chapter, and we have a lot of presentations about that. I'm also the faculty advisor for the Formula SAE. If you saw the presentation with Dr. Ayala, I think it was last week, he's the advisor for those two cars in that back row there in that picture, and I'm the advisor for the two cars in the front. So we work together in the lab making race cars with students. So it's very, very fun. So a lot of universities have that. If you come to ODU, we do have that. So those are the main things I do. Now, before we get into the heat transfer thing, let me briefly talk about the program. And while I'm doing this, I apologize if I go a little fast. I'm a fast talker. So, please feel free to send me emails and questions if you're not sure. We're going to save some time at the end to make sure we address them all if we can. So one of the main things many of you may not be aware of, especially if you're international. I don't know how many of you are in the US right now. Those of you that are international, it's not as common to have a technology program as far as I'm aware. It began in the US a long time ago. We won't get into all the details on that, but engineering technology is basically just the more applied version of engineering. So engineering is really science-based these days, really intense. It's meant to prepare you to go to graduate school and develop and design new intense theories and designs and tools and ways to solve problems and things like that. Well, someone has to actually implement those things, and that's what engineering technology does. It's basically the exact same thing as engineering in terms of the curriculum, minus the advanced math. We only go to Calculus 1 because most industry only requires up through algebra and trigonometry. You got to be very good with those things, but that's what most engineers use in the field. And what that field is we do a lot of stuff in HVAC, ASHRAE. We do a lot of stuff with material science, automotive industry, and again, these are industries where you're going to have mechanical engineers. I'm talking from mechanical side because that's what I do, and mechanical engineering technology. I actually was an undergrad in mechanical engineering technology and went to graduate school in mechanical engineering. And now I teach in mechanical technology because that's what I prefer. I prefer getting things done rather than thinking about, developing new things. I did that for a while in the aerospace industry before I came to ODU. I was worked for Lockheed Martin for a number of years and Swales Aerospace, and then I came over here. We do things in manufacturing. There's a lot of manufacturing that engineering technology graduates get involved with. Marine engineering, a lot of it here. Now, it's big here because we're Hampton Roads. We got the Huntington Ingalls Shipyard. We got the Norfolk Naval Shipyard. We have a Kelowna Shipyard. We have a lot of shipyards because, as many of you probably know, we are on the water. We have a huge port, big ice-free port, you know, for bringing in goods. So marine is everywhere, and it requires a lot of engineers. Robotics and automation is a big thing. That's a big part of manufacturing as well. Any manufacturing plant these days is going to have a lot of robotics and automation to make it happen. So there's a lot of that mixing together. Power production and energy management. Anytime a building is built, someone has to go back to it and make sure that all the power requiring devices, primarily HVAC, is working properly. Are the fans wired up properly so they're blowing air through the ducts the right way? Are the lights that are automated not, you know, they automated with the right timer so they're not on at the wrong time? So much energy is consumed in buildings. And so ASHRAE and AEE, I've got them kind of bookended here. They're very much hand in hand. You don't have a building designed with ASHRAE without having an AEE engineer come behind it when it's all done in order to do an energy, we call it energy audit, when you commission a building to make sure that everything's working right. Big things engineering technology graduates do, mainly because we're applying, these things apply what engineer and industry needs right now. And that's where engineering technology graduates are primarily trained for. So that's a very brief rundown of the kind of fields that, now there's a lot of others out there I'm in fields that engineers get involved in, but these are primary fields in the Hampton Roads area where a lot of my students go to work in. Automotive is a little bit less than some of the others just because we don't have a big automotive industry in this area, but it does exist. And this is a brief spectrum of what you would expect as an engineering technology graduate versus an engineering graduate. And we're not even talking about graduate school right now. This is just basic undergraduate degree. If you do want to go to graduate school in engineering, I always recommend going mechanical engineering or civil electrical, basically going the electrical or the engineering route, because that's going to prepare you with all the math classes. Engineering graduates take Calculus 1, Calculus 2, get my hand in the right thing here, Calculus 3, and ordinary differential equations. And then once you go to graduate school, you got to take partial differential equations 1, and usually part 2, sometimes part 3. A lot of math. Engineering technology graduates, Calculus 1. And then we have a course applying that, but it's not so, you don't get too advanced because, again, you don't need so much. So engineering technology. Now, that distribution in sales, honestly, on the very far left there, almost every engineer I've met in sales is a mechanical or electrical engineer graduate, not an engineering technology graduate. I don't know why that is, and I don't know why it's off to the left right there. But most of my graduates get involved in production engineering, manufacturing, component design, test and evaluation, and the management. The president of the Toyota manufacturing plant, the largest Toyota manufacturing plant, I think it was in Kentucky. He's retired now, but he was an ODU MET graduate from the 80s. He was the president of the Toyota manufacturing in either Kentucky or Georgia in the U.S. But at the time, it was the largest Toyota manufacturing plant in the U.S. ODU MET graduate. So I think that the reason a lot of engineering technology graduates get into management is that, at least from ODU, our program requires a minor, and most of our engineering technology graduates get a minor in engineering management, mainly because there's no extra math requirements there. So we don't actually train you to be management in our program, but that's what you can expect. And then off to the right, more engineers are going to be theoretical, complex design analysis, things like that. Now, again, none of this stuff is set in stone. I have engineering technology graduates who get into theoretical research. Usually they learn that in their field, but it just depends on, we're not preparing for that from graduation. So let's pause and take a question. What should you do when you want to do aerospace, but you're not from America and your home country doesn't really have a good program, space, military, aviation program? For that, that's a good question. I would say you would want to look into taking school as an international student. We have a lot of international students at ODU. I have a lot of international students in the mechanical engineering technology program. I think a lot of that is because there's not really a technology program outside the US. So I would say you want to look into an international program. Feel free to send me an email. I can at least maybe point you to some right people. We have an aerospace program at the university at ODU, and I can point you to contact there. I'm not trying to sell you on our program because it's not my program, but I'm sure they can point you to who would be some good resources out there, especially depending on where you live. How do you not die from all the math involved in engineering? That's a very good question. I personally love math. When I was an undergraduate, I did MET because mechanical engineering technology, because I did not want to do the math out of high school. I got through trigonometry and I was done. I got through calculus 1 barely. I got a C minus in calculus 1. but they let me slide through with it because you need to see her better in it. That was 25 years ago. But after my bachelor's degree, I learned how to learn. You learn a lot of college is not necessarily just memorizing things; it's learning how to learn things. And then I went back and took all the math, calculus 2, calculus 3, ordinary differential, and partial differential, and I loved it. I went all the way up to partial differential 3 because I really, really loved it. No, I don't use it in what I do as an MET professor. I stick with the trigonometry and algebra, but I did use it when I first went into industry working in aerospace. So again, I suggest to students who, if you like engineering, but you're not keen on the math, engineering technology is where you want to be. The jobs are very similar, the pay is very similar, but you are going to be doing more applied, less than theoretical. And if you want to be on the cutting edge of things, you're going to need that math and that engineering degree. Want to build cool stuff is a good reason to become an engineer. Very much a good reason. Because before you build it, I mean, you can build things in your shed. A lot of amazing inventions have been developed by people who are not trained engineers. Being trained engineer is not required to develop and build cool stuff. But if you want to really understand why things work and then build upon that knowledge, engineering is where it's at. Whether it's engineering technology or pure engineering, which is really more engineering science. But I love it. I can't get enough of it. I tinker. I've taught myself so many things. I've got my wall behind me, that ODU thing behind me, but I've got a room full of stuff that I like to work with. All right, so I'm going to keep on moving. If there's more questions, we'll pause for them. So at ODU, just very briefly, we are ABET accredited. ABET is an international thing. It's basically it is the Accrediting Board of Engineering and Technology. There's two parts. There's TAC of ABET, which is technology accreditation, and there's EAC ABET, which is engineering accreditation. Engineering is for the engineering program. TAC is for engineering technology is for the technology program. Basically, what it means in the U.S. at least is that you can sit for your fundamentals of engineering exam to get your engineering and training certification, which is what most engineers do right after they graduate. I highly recommend it, especially if you're a technology graduate. And then you can sit for your professional engineering licensure in 5 years. Now, outside the U.S., things are different. ABET is coming. I know there's a lot of South American universities with ABET accreditation. I know some European universities, but it's not as prevalent as in the U.S. because every country has their own licensing program for engineers. But in the U.S., if you want to ever sign off on engineering drawings, you ever want to go to court for being an expert witness, you ever want to run your own company and have your name on the door, you need to have a PE license to be a professional engineer. And to do that, you have to have your EIT, which you had to get that. You have to graduate from ABET accredited university. We have about 350 full and part-time undergraduates in the mechanical engineering technology program. In the engineering technology department, which is mechanical, electrical, and civil, we have about 800, 900 undergraduate students. We do not have a graduate program because the technology is not training you for grad school. It's training you to get out there and be an engineer. So that's our basic program. We have a lot of distance students. We have been running distance learning education since the 80s. We are, the technology program at ODU we were at the forefront of technology education at the university. We've been doing it forever. We have international, we have local, we have all around the US, a lot of students. And articulation agreement, fancy word for, we have programs where if you complete, a 2-year associate's degree at community colleges, you come in, you get your first 2 years automatically waived. We do package deals. It basically makes it easier to transfer from a 2-year community college to the 4-year program and save yourself some credits. Now we have a few outside the state of Virginia, but most of them are within Virginia. It's just the way it is. Doesn't mean we don't have others that we can't develop. We just don't. If you're outside the state of Virginia, it does not mean at all that you can't take courses here. Obviously, we have students from all over the U.S. and the world. It's just that if you're in Virginia, we have articulation agreements. If you're planning to do community college, save some money, highly recommended. We have ways to do that very, very, very simply. And then U.S. Navy Power School, we have a lot of military graduates. As an MET student, we have concentrations at ODU. Basically, these are the core focus of your curriculum. Everyone takes the same courses up through the 300 level in junior year, and then you can focus on certain topics at your upper level. And I'm going to briefly burn through this because I do want to get into the heat transfer, and this is all going to be on Blackboard. Have a link to the website in a bit. We have manufacturing concentration, which is basically you take 4 senior electives, 400 level courses focused on this, and you can do your senior capstone project on this as well. Most engineering programs in the US are similar to this, just different concentrations. We have manufacturing, mechanical systems, mechatronic systems, marine systems, and nuclear systems. Now this is really only available to Navy nuclear graduates, Navy nuclear power school graduates, and Dominion power school graduates, because we don't have a nuclear reactor on campus to give you hands-on with this. Everything else, we have a lot of labs for that. So we can't graduate engineering technology graduates saying they know how to do this by hand if they haven't already done it by hand in industry. So this is a very focused thing, but it's very cool for those that do it. And then here's a link for more information. Again, this is going to be on the Blackboard link. I'm going to give you that link in chat. And once we're done with this at the end of the next presentation, so you can go there. Same place you probably went for Dr. Ayala's. Well, it is the same place you went for Dr. Ayala's stuff. And Professor Escobales as well, if you've seen his. So again, this is a lot of information. When we're done with this, at the very beginning of the slides, you have my email. Feel free to email me. Please email me. I'm happy to answer any email you have about things. I'm always available. And I can give you more information. You can do a one-on-one Zoom session if you're more curious about our program or engineering in general after the session. So that is very brief. And again, I did that quickly because we have an hour. I do want to get into what I think is the fun stuff. If there's any questions about this, feel free to keep asking them. And when we get into the next thing, I will pause and re-answer them. I don't want to leave any questions out. But I want to dedicate a solid 30 minutes to the next section, so we can then go to Blackboard and see what we're going to do with it. Because there's going to be a hands-on activity that you're going to do after here if you like, and a spreadsheet you can fill out and you can send to me afterwards, and I can give you feedback on it. So let me first stop sharing this and pull up the heat transfer introduction. I get excited about heat transfer. When you get to graduate school as a mechanical engineer, you have options. They call it the wet side and the dry side. Dry side is dynamics, kinematics, basically motion of bodies. Wet side is fluid mechanics, and that's what I did, and I love it. Nothing like thermodynamics, fluid mechanics, heat transfer. Now, there's also the math intensive stuff, so a lot of students can't stand it, but if you learn to love it, you'll know what I mean. So let me get to my share here again. Contact information. So I will put that here in the thing here. So I just, so I think my the email's at the beginning of that PowerPoint, but I just included it. It'll be shared with you in a Q&A in a minute, I'm sure. And then you can email me whenever you like. Let's see. So I don't need that yet. I am trying to share the heat transfer. All right. Now we're going to slow down a bit. Thermodynamics part 1. Thermodynamics is sometimes a scary word for a lot of students. And a lot of so as a program director and be a part of university and part of engineering program, we have an industry advisory board, which basically we have professional engineers from all around the state of Virginia that we meet with twice a year, so we can make sure that our curriculum is delivering what industry needs at the moment. And we can plan for the next 10 years because they know where industry is going in 10 years from their own experience. They always tell me that thermodynamics was their least favorite. Most engineers didn't like it. But it's everywhere, right? All it really is the science of energy and how energy is stored in one form and converted to another, or moved from one place to another, whether that's through work or heat transfer. And energy is basically the potential to do work. There's a lot more to it than that in terms of using that in science and then the equation, but basic, it's just potential to do work. Things vibrate and translate and rotate at the particle level, and that all combined together is energy, and it can do things. We're not going to get into all that. We're going to get into the heat transfer part today. Heat transfer is everywhere. As a thermodynamics student, Thermo 1, you're going to study work and heat, and you're going to study the difference between the two of them. Very, very important. They're basically both ways of moving energy from one place to another. Work is a way, is basically the ability to move an object or move a weight some distance, whether it's vertically, horizontally, whatever. Work is force times distance, right? You probably remember that from physics if you've taken that. It's the ability it's energy, moving an object. Heat is the movement of energy due solely to a temperature difference. We're all used to that. We touch things. You touch a hot cup of coffee. Maybe you just, pull it out of the microwave, a mug, and it burns and you say it's hot. Well, what it really is you're feeling the result of the high energy particles in that cup or that fluid and the cup that got heated up in the microwave, and they're in contact with the lower energy molecules in your hand or particles in your hand, and you're feeling that energy transfer. And our body and our nerves sense that as hot. That's heat transfer. That's all it is, right? We're not going to get into the temperature scales and all those things because we have to measure hot relative to something. That's not for this class or this thing, but it's basically motion of energy from one place to another due to temperature difference. The unit for energy in the SI is joule. That's the basic unit. Again, where that comes from, we don't need to get into that today. You can Google that. It's a basic SI unit of energy. SI metric system. The rate of energy transfer is the watt. How many joules of energy can you move in 1 second? All right. So basic units right there. And I'm throwing them out there because the spreadsheet we're going to do is going to have some units in there. And what we're going to talk about, though, is modes of heat transfer. There's 3 ways that energy can transfer via heat. You're probably familiar with them, but you may not have names for them all. Conduction is the way when it moves through a solid object. So if you've got that cup of hot water coming out of the microwave, the heat transfers through that maybe ceramic, most likely a ceramic mug that got to your hand. That was due to conduction. It conducted from the hot liquid through the mug. You've got convection in a gas or a liquid. When things heat up, you have the density change, and density change causes motion in the fluid. That leads to fluid moving, and colder fluid replenishing the hot fluid. So you have motion. That's convection. Or when you blow air over, past a surface, you're blowing air. It's receiving energy and then carrying it with it, and it's again replacing itself with cooler air, and then it received energy again from the hot surface. That's convection. Energy due to heat transfer in a moving fluid, whether it's gas or liquid. And finally, you have radiation. That's the energy due to the it's electromagnetic waves, photons moving through a vacuum or a medium. That's how we get heat from the sun. It's how when you stand by a fire that's you're far away from the fire, you're feeling radiation. There's a bit of conduction and convection through the air, but it's primarily radiation. Everything emits radiation heat, heat due to radiation because it has a temperature difference, if it has a temperature difference from something else. But usually it's very small unless it's something like a fire or the sun or, a burner. It has to be very, very hot for that to matter. But again, those are the 3 modes. Radiation is very mathematically complex. Convection is very, very hard to, it's very I should say the right way, specific, I guess. There's no analytical equation really for it. You have to do a lot of experimental correlations to come up with what is the convection coefficient in equations. Conduction is pure math in a partial differential equation, pure calculus. But we're going to simplify it. So why do we even talk about it? Because it's everywhere. You got a house. You're going to have a lot of heat transfer. You're going to have conduction through the roof, through the windows, through the floor. Drafts carry heat out the window through convection. You got conduction through the walls. We have to insulate these things. ASHRAE standards tells us a lot of how much insulation we have to do, but it's everywhere. We got to deal with that. There's heat transfer there. Heat transfer in automobile engines. One day we're going to go all electric. There's still going to be heat transfer because electricity, there's going to be heat created through all of the, devices there as well. But right now, most engines are still, gasoline or diesel, and they're mechanical components. Mechanical components expand, they contract when they heat and cool. They melt. The temperature inside of a combustion chamber is really, really, really hot. The max temperature of combustion when you burn gasoline in a cylinder is around 2200 degrees Celsius. And exhaust is 1000 degrees Celsius. Materials melt much cooler than that. Now, that's not constant temperature because it's happening cyclically. You have burn, exhaust, burn, exhaust, burn, exhaust. So you're not constantly at that high temperature. But if we didn't cool things off, if they didn't melt, they would at least expand and seize up before things melted. So we have problems. We have to keep things cool. So we have coolant. Very, very critical in automobile design. Anything involving combustion. In metals. So we anneal metals. Annealing is a heat treatment process to restore some of the ideal metal properties that were damaged during manufacturing. When you weld things or you bend things or you extrude things, you usually end up making them more brittle. And it has to do with how the molecular structure is manipulated when that happens. I'm not a metallurgist or a weldologist. I call it that way. But that's, if you're in material, it's a big thing. So annealing is very, very important. We have so many things are involved welding, involved extruding, involved stamping. So it's just a heat treatment process to improve its machinability and other ideal behaviors. Because it's too brittle, it'll just break when you hit it with a hammer. We don't want that. That's like ceramic tiles, right? Not ideal. Very, very important and critical. Which, by the way, in the MET program, we also have a new welding lab. We do a lot of welding. We have a good welding faculty at ODU. He's great. Very important industry. And we're not just talking about learning how to weld. It's like, oh, when do you do certain types of welds? There's so much science involving in welding, not just taking your stick and making a seam. Heat exchangers, oh my, these are everywhere. You got an air conditioner outside your house. You've probably seen that big old box out there. That's a heat exchanger. If you live in a country where maybe you don't, it's cooler or it's warmer, or maybe you have evaporative coolers or whatever devices you have to keep the building cool, it's some form of a heat exchanger, whether or not it's plugged into the wall. A heat exchanger is just a device to exchange energy from one fluid to another. So you can cool off one area because it's gotten too hot, right? You have radiators, you've got HVAC systems, you've got the condensers and steam power plants. They are everywhere. We got to deal with that. But we're not going to get too much detail on any of these right now. These all involve conduction, convection, and radiation. We're going to talk about one specific application, conduction heat transfer, and the basic equation for it. So conduction can happen in liquids and gases, and it does, but it's primarily something we talk about in solids, because liquids and gases usually move, and when they start moving, we're talking more about convection. But we're not going to get into the details yet. We're just going to talk about solids right now. Conduction is a result of high energy molecules interacting with lower energy molecules. All right. Basically, think of a pool ball on the pool table. If you've got a bunch of balls that are moving rapidly, you just hit them, they're going to bang into the stationary ones, and they're going to move a bit. They're going to move a little bit less, but they're going to move. If they hit something else, they're going to move a bit. They're transferring energy. Now, that's kinetic and potential energy being transferred. But if you think about it on a small scale, the energy transfer between particles and molecules is kinetic and potential. But then at the large scale, we see that as conduction, heat transfer. That's stuff you'd study in an advanced thermodynamics in graduate school, which we're not going to get into. So in liquids and solids, gases, due to the molecules colliding into each other. In solids, due to them vibrating, because we have lattice structure in solids. This is more of a chemistry thing, material science. But again, it has to do with the energy being transferred between things. Now, there is an equation to govern that. Now, there's also a thermodynamic property to govern that as well. Everything has a thermodynamic property that engineers have discovered. We've found ways to measure things, and we've applied concepts to them in terms, and we say this is a property of the substance. Materials, depending on the materials, molecular makeup, how it's structured, all that jazz, the molecules will exchange energy with each other at different rates. That property is called thermal conductivity, okay? Most engineering books use the lowercase symbol k for that. It can vary. So as an engineer, especially if you're outside the US, I'm familiar only with what the US textbooks use. You just have to know what the nomenclature is. What is the author using, and what does everybody you're working with use for the symbol, so you know the right symbol to use. That is not really important. What's important is what the property is and the units on the property. So for example, brass at room temperature, 120 degrees Celsius, is a thermal conductivity of 113 watts per meter Celsius. What that means is that if you've got a 1 meter wide, say, slab of brass, and you got a 1 temperature difference on either side. So one side is 99 degrees Celsius, one side is 98 degrees Celsius. 1 temperature difference, 1 meter long, 1 joule of energy is going to get through that in 1 second. That's a long way of saying that when you look at the units, because a watt is a joule per second. So it basically just means the rate at which energy will travel through there. So, and I should say 113 joules will travel through there per second, because that's 113 watts per meter degree Celsius. So you get energy flow through there at a rate of 113 watts. It's from 1 meter slab and 1 degree Celsius difference. That's what the units are telling you. But again, that's stuff you'll learn more about as an engineer or physics. All materials have that. Now, a law, which is basically an equation that was developed by Mr. Fourier a long time ago. If you ever learned Fourier transforms in math, you get to that same fella. It's basically he observed phenomena, applied an equation to it, and wait a minute, look, this equation works if we put this thermodynamic property, thermal conductivity in the front of it. All right. We're gonna get to the equation in a minute, but for starters, it's a very ugly equation. Well, I shouldn't say that. If you like math, it's a beautiful equation. If you don't like math, it's an ugly equation. If you're ambivalent to math and just do it because it's a tool required, then you'll probably enjoy it enough if you simplify it down. So Fourier's law basically is a way to predict and model heat transfer in all directions, whether steady or unsteady. It just means it can be very complex. we're going to simplify it. We're not going to get into that entire thing. As an undergraduate student, you really wouldn't get beyond maybe 3 dimensions of conduction. It's just very complex. But in the first semester thermodynamics course, you're going to look at it in 1 dimension. Very simple, constant heat flow being supplied, because it just gets very complex mathematically to do more, okay? So if you do that, very simple, heat transfer in 1 direction. Example of that would be a big wall, right? In reality, yes, heat transfer is going to flow in all different directions, but as engineers, we simplify things down so we can better approximate them with simple equations so we can understand how things happen. And if we're off by a little bit, it doesn't really matter. Engineering, 5–10% error is expected. It's hard to get exact because everything in engineering is based off of measured properties. Rulers aren't very accurate. Our eyeballs aren't very accurate. We can't measure things with perfect precision. So we try to keep things within 10% error, which means we can make a pretty reasonable approximation of 1 dimension a lot of times. So the equation is there. What is that equation? K is the thermal conductivity. A is the cross-sectional area of the material. So if you're looking at a wall and you got a hot outside and a cold inside, you got heat transfer from the outside of the house into the house. The area of that wall that you're looking at is the A. The K is the thermal conductivity of the wall material. Now, maybe a composite wall with a lot of different materials, well, then it gets more complex, but it's still this basic equation. dt dx is the temperature slope. We call it the gradient, but you can think of it as the slope. Temperature outside, temperature inside, the slope if you were to plot a line. It gets very complex if this is non-1D. It gets very complex if you have, non-uniform materials, but we're going to look at it very simply. dt dx, the change of temperature versus distance from the heat source, is just a temperature gradient. Think of a slope on a line graph, but it's not always going to be linear. It depends on a lot of things. You'll learn that in engineering. All these things depend on a lot of things. Let me pull up something here. I'm hoping, so I just realized that my chat was minimized. So let me see if I missed any questions in this meantime here. Give me a second here, everybody. There we go. All right. So there's a good question right there. I apologize that I missed it. How do you feel about the approximation slander from physicists? I think or did that go down here? Let's see. I'm assuming you mean when physicists talk smack about engineers approximating things. I say that's fine. It's important to be very, very precise on some things, but someone's got to make it happen. And until they can give us a perfectly measuring ruler, I'm assuming this is what you're asking about. If they can find a way for us to develop rulers and measuring devices that are so precise, and then cutting tools that are so precise, and machining tools that are so precise that we can actually produce something down to 0.00001 inch precision at all times in a reasonably cost-effective way, then they get something to talk about. But we can't do this. I mean, imagine this, a building. You're gonna calculate the weight of a support beam that's required. You're going to first tape off the support beam length with measure it with a measuring tape, mark it with a piece of chalk, and cut it with a really wide angle grinder blade. How accurate can you possibly be? We can only be within certain accuracy, right? Because these things have to get built one day. Now, there are some applications that think you must be very, very precise, but there are many applications where 10% error is well within the realm of reasonability. So not a problem at all. Physicists can talk about that all day long. They're very, very important for us. They do all the accurate thought processes. Of course, if physicists doing astrophysics, they're extremely off, right? There's, being, millions of miles off isn't really a big deal if you're an astrophysicist. So it all depends on the scale of what you're doing. There are some engineering applications that must be extremely precise, but many of them do not, and they're just not cost effective. So what's the most coolest thing I ever built? Well, I didn't build it, but what I did before I became an ODU faculty member was I worked at Swales Aerospace for starters, then Lockheed Martin. And when I was doing that, we were working on radiation and micrometeoroid mitigation team. So when you send things into space, space is not empty. There's little particles of things flying through space that would just shoot through space material. You have to design the hull that's able to withstand that, but you also have to deal with the radiation that's everywhere in space that will just fry your heart in a heartbeat. Now, we could insulate a space vehicle with water bladders. Hydrogen is a great way to mitigate that, but the problem is very heavy. So we have to find ways to intelligently arrange the radiation shielding based on the application. If you're just flying to Mars, okay, then where's the sun going to be coming at you? You got to do it right. If you're going to be a Mars base or a moon base, where do you want to put the radiation to protect the equipment and the astronauts? So I worked on that. It was great. We did CAD models, we did solid, we put little particles in there, we ran models of environmental models, and we helped develop where radiation should be on things. That was fun. And the second most coolest thing I ever do is the race cars. I love it. My own personal stuff, I built CNC direct drive wheels for sim racing and stuff. I like that too. So a lot of fun stuff. And a lot of it requires heat transfer. So, oh shoot, some reason my chat is not staying up when I touch on my screen. Huh, this is not what I wanted. Chat. All right, please back up again. I am not sure why my chat does not want to stay on my screen. So I just have to keep on coming back to it. It's just really weird. So I'll come back to it in a bit. But let's go ahead and get to this, and then we'll get into the blackboard, and we'll go into more questions then. So constant property heat transfer, conduction, very simple equation. If you make a bunch of assumptions, we're not going to get into all the details, but an activity you're going to use that has this equation in there. It's actually going to do all the math for you, but you can do this yourself. Very simple algebraic equation. The temperature difference between two sides of an object divided by the distance between those 2 points times the thermodynamic property of the material, decay, and the cross-sectional area gives you the heat transfer. That negative sign is simply for thermodynamic sign convention. We define positive heat transfer in the direction of decreasing temperature. So you got to put that sign in there because T2 is lower than T1. Don't sweat the details on that. The activity I've got for you, all you got to do is do the activity, enter the numbers in the spreadsheet, it gives you the results. Now you can, if you are a little more mathematically advanced and you want to do that, then I also have an activity for you to do that yourself, but we'll get there. When it's flat wall, it's a bit more complex. So if it's a circular disc, which is another part of the activity, you get a bit more complex equation. That natural log, this all comes from this equation. We have to, hold up. Mathematically, we have to integrate that equation. Oh, integration. Oh. Unless you've done the calculus one, you may not be familiar with it. It's not that big of a deal if you know how to do it, but you separate variables, you got to integrate. It's not always the funnest thing in the world, but that's how you do it. If we make some simplifications, it becomes very simple, and the integration is that equation for a 2D wall. This is not a math class, we're not getting into that. But if it's a radial body where the area increases as you move out from the center, the integration leaves you with a natural log, radius stuff. It's a little bit ugly, but we'll get into application of that in a minute. Again, I'm burning through a little bit because I want to have time for questions in the Blackboard thing. But in the end, these are the two equations that you would use. And these are the two equations this activity we're going to do makes use of in the spreadsheet for a linear conduction and a radial conduction. So what is this activity? Well, because we have students that live internationally, we have students that live all over the state of Virginia, and because we've had COVID for the last year and a half, our labs had to be online for everybody the last year and a half. But normally, the local students on campus do this experiment in class, in the lab room, take the measurements and everything. But if you're distant, you have to do online activities. We developed this, and what you're going to be doing is I've got the snippet from the actual activity and the intro video for you to watch on your own after today's presentation, anytime between now and I think the end of the REYES program. You can go back and do it, which is what you would be doing if you were an ODU student distance. There's more to it in writing the lab report if you're an actual engineering student, but the lab activity is going to come from that. The equations used are these. Now, the important part here is these equations are, the equation over here that we looked at previously is if K is constant, you can solve for the heat transfer. But K is not constant. K changes. Thermal conductivity is a function of the material's temperature. So this experiment is meant to determine that thermal conductivity as a function of temperature because it does vary. You can see the thermal conductivity trends of different materials and how it changes with temperature. You can study this on your own afterwards. Most metals drop a bit. Brass climbs a bit. Brass is the one metal, one of the more common metals that the thermal conductivity increases with increased temperature rather than dropping. Most gases increase, but some of them change. Liquids do. Again, you can just see the trends here. We want to determine what is the thermal conductivity of brass as its temperature drops from the heat source to the cooling source. And we have an experimental setup that does that. If you can measure the temperature at a bunch of fairly closely separated sections, you can use these equations to calculate the approximate thermal conductivity in those sections, and then you can plot its trend through the material as a function of temperature if you're supplying a fixed amount of heat transfer, which we do. And we do that through this apparatus. This is just a sketch. We've got a heat transfer unit. The linear unit is a core, brass core with a heater on one side and cooling on the other. We've got these little thermocouples at 10 millimeter distances from each other, and we can measure the temperature at each location. Measure the temperature at each location with a known heat supply on the heater side and a cool water on this side. You have a temperature difference, so heat transfer flows through there. If we know the brass has a diameter of 25 millimeters, we can calculate the area, and we can plot, or we can calculate K, thermal conductivity, and then plot thermal conductivity as a function of temperature. For the radio, we have a flat disc sandwiched. Oh, back to this again. That white stuff all around it is insulation. Insulation is meant to try our best to make sure it's one-dimensional heat transfer. Yes, it's going to be warm on the outside. It's not purely one-dimensional, but it's mostly one-dimensional with enough insulation surrounding that brass cylinder. The radiation is a flat disc, 4 millimeters thick, that's sandwiched between material top and bottom. And you can see that here. On the radio unit, you've got this is the side unit. You get this big insulation on the bottom and the top. But the disc is sandwiched between there with a heater core in the center and cooling water wrapped around it in this little metal pipe wrapping around it. And those are separated 10 millimeters apart starting from the center. And there's a heater core resistor in the center that's receiving electrical power from the electric socket, turning into heat. And it's moving through the system because we have a temperature difference created by that cold water running through that outer wrap. All right, so what we're going to do is the activity is going to have you measure the temperature at those different locations in the linear and the radial. You're going to enter this in a spreadsheet that I've already developed, and it's going to output the results. Now, I've got a few steps for you to do to make it a bit more advanced for yourself if you like, but you can use the spreadsheet as a check to see if you've got it right. So we're going to go to Blackboard. I'm going to copy and paste this in the chat. So you can, because you're going to need to go here. So you don't need to go there right now. If you have a computer, feel free to do it. This should work. It worked for Dr. Ayala's class. This is a Blackboard organization that we created. I'm getting my chat up. That we created that. Let me chat up again. Why is my chat not showing up? Oh, it's over here. There we go. So now I got things up. So yes. Shida, I did receive both those questions 5 and 6 and 4. Yep, I got all your questions. It looks like. And I'm pretty sure I've addressed them all. But the problem was I couldn't get the chat to show up when I had the PowerPoint open all for some reason. I don't know why. So I'm going to copy and paste this in here. If you can share that with everybody, Shida. That is the link for the Blackboard. It should not require a login. It should work. If it doesn't, feel free to send me an email, and I will try and get it to work for you. But I know we had some issues with it not always working. So I'm going to go there now. I'm going to just click on it. I'm going to close this out. I'm going to share my screen. All right, so let me share my screen in a minute here. Blackboard. All right. So I got so that link should take you here. If it doesn't, send me an email, and we'll, afterwards we'll try and figure it out. I'll put you in contact with somebody who should be able to help out, but it should work. Try it more than once. If it doesn't work immediately, try it in the browser. There should be no login. This is the REYES for engineering stuff. I've got a few things here. Let me put this actually in preview mode so you can see what you would be seeing. All right, let's see. A few different links here. Thermodynamic lab activities is what we're doing today. These are some other links here. Again, you can go through there. Don't need to sweat them right now. I don't know if everything here, these are all things that will be covered by the other professors. For me, I'm doing the thermodynamics lab activities. I've also got that PowerPoint that I went over with the MET stuff. So you can see here, this got my link. This is the PowerPoint information from earlier. There's more information here that you can read through. Feel free to do that. We're going to talk about this Thermo Part 1 conduction heat transfer. There'll be another link for next week related to Part 2, but thermodynamic lab activity, Part 1. I've got a few things here. This PDF is a presentation I just went through. So I know I went through it fast, but all the information there, you can read through it. What I want you to do on your own is, here's a short video. This is me going through the apparatus, explaining it in more detail. This is what the engineering students at ODU see before they run the experiment. And no, the link does not require login. This is an open guest organization. It does not require a university link. That link I shared was sent to me by CLT, saying, and they say it should be no login. If someone needs a login, please email me after this, and I will get you in contact. After this class, I've got a class till 4 o'clock, so I won't be able to reply till later. So if it's not working, please try again. I do know that Dr. Yala had some issues, and then this was what was sent just the other day from CLT. We'll get it to work. It should work, but I understand if it's not working, just please send me an email and I will share it with whoever. So let me see. I don't know if it's possible to get the list of everybody who was involved in today. I will get that working best I can. I clicked on it, it worked. I know I log into ODU, but still, I did the other day on a non-logged-in computer. So we'll get it to work. But you can at least see where I'm going to point you to, and then we'll make this happen. There's a short video you'll be able to watch.
What we have here is the conduction heat transfer.
I developed this a number of years ago, so I look a bit younger there. You'll watch it on your own. It's only 4 minutes. Then we've got step 2, complete the heat transfer experiment. So what I've got here is this experiment. What you're going to do, if you click on it, it's going to basically walk you through some steps. You'll read through the instructions carefully, and then you're going to click what it tells you to do. So you'll click next. You're going to, for example, it'll ask you to select and adjust a heater switch. Let's see, temperature knob, power knob, When you be asked to adjust, hover the mouse and click there, click next to continue. You're going to select this, and let's see, you're going to select, linear conduction, right? So you're going to go through it like that, step by step, the experiment. I'm not going to spoil it for you. We'll get it working if it's not working. And then you're going to enter the data. So please download the spreadsheet before you start the activity and input the recorded data in the blue cells, follow the instructions in the green cells to present your results. And then for additional practice, you see if you can reproduce the calculated output in the peach cells. Information here is important. The geometry. This spreadsheet, I'm going to share this spreadsheet real quick. So let me stop sharing and then share screen. The spreadsheet. This spreadsheet is not cell protected. So if you start clicking on it and deleting things, you'll ruin it. You'll need to re-download a fresh one. So be aware of that. These are just samples. What I've got here is you're going to input information in all these blue cells. These other cells will not give you a result until you've entered all the required blue information. Once you do, it outputs the results, approximate thermal conductivity between the measuring points using these equations up here. It does all the calculations for you because, again, you haven't taken Thermo 1, so you aren't at the math level for to develop this, to do this. You may not know how to use Excel yet, which is understandable. So all you do is enter numbers directly in these blue cells. If you enter the wrong thing, things won't work. Or if you enter letters or whatever, they won't work. If things don't work, delete the spreadsheet and re-download it again. And then for practice, if you want to, you can produce these graphs down here. All right. You'll see thermal conductivity, or the temperature drops through the material, and thermal conductivity is fairly flat. It doesn't really change that much because the temperature difference is not very much. But again, you can see it's experimental. So the points fluctuate. Doesn't mean that thermal conductivity fluctuates. It's all over the place because it's an experimental procedure. Again, go to the video and you can download this and do the activity. What engineering students do is they're not given the spreadsheet. They do the experiment. They're given some guidelines. They have to create a professional spreadsheet, engineering spreadsheet. They have to do the calculations. They have to produce the graphs. They have to do a thorough discussion, analysis of results based on what they studied in the coursework and correlate it to what they did in the lab and discuss why are things not exactly what they expected. And that's just learning to take engineering theory and see it in reality and understand that things don't work like you think they do in theory, because there's a lot of real things that we can't account for, especially at the undergraduate level. So I'm going to leave that for you to have. Don't say I'm not saving it. I'm going to go back to Blackboard. And so this, again, it's not for submission, but feel free to contact me with emails if you want me to look at what you did. If you have questions about it, I'm happy to answer those. And now I'm going to take a pause, pull up the chat. and see what kind of questions we have. Again, this is very simple. I know I didn't give you tons of context. It's not a lot of time for it, but this is just one experiment. As an engineering student, we also have a heat transfer experiment. We have steam power plant experiment. We have gas turbines, ramjets, a bunch of experiments. It's just one application that you do. And this is actually a really neat unit because you can actually, when you do it, you watch the video, I unclamp that linear core and there's a little insert in the middle. You can pull that out, put a little thin piece of material inside there, usually ideally less than a few millimeters, and then you can sandwich it, measure the temperature on either side, and that's how you can experimentally determine the thermal conductivity of an unknown material. And you can use that for future designs. But again, so I don't know if this is working yet. Shai, have you heard from anybody if they got it to work yet? But again, and if not, don't worry, we'll get this to work. I just need to reach out to CLT and find out what's going on. Let me click on that link I copied into today, make sure I copied the right link. All right, so if you cannot log in, it sounds like you can't, that's fine. I will reach out to CLT, we'll get it to work. It's available through the end of the summer, so there's plenty of time to do this. If you do it in 3 weeks, that's fine. It's really just a chance for you to see what the engineers do here and get a feel for engineering numbers. But unfortunately, I don't know why it's not working. We've been working with CLT for 3 weeks, and I know the fluids one had issues. I just clicked on that and it worked again, but we'll get it happening. But in the meantime, any questions for me at all? I know I zoomed through that, but again, we got an hour. We don't have all day to do it. Any questions about engineering in general? Anything that you've got a question about? You want to be a student? Ah! A student said it's working. Awesome. So that means it does work. If you're not getting it to work, please try a different browser, because if one student's got it working, then we know it works. Try different browsers. I use Firefox. That's what CLT, I think they recommend Firefox. I think you can try Chrome, Edge, Opera. I'm sure in different countries you might have different browsers, but it should work. I used the same link last summer, and we had students from all over the world as well, and it got it to work. So just please check. All right, I have a Peltier module and willing to make a simple air conditioner. I want to calculate its efficiency, and I want to know why does it have low efficiency in terms of its design. Okay, that's a very good question. So first of all, coolers, we call it coefficients of performance, but it's basically efficiency. When you study thermodynamics, there's a concept called reversible processes. A reversible process is a process that is not real, but it's a process that does not generate any losses. For example, take your hand, rub it on the desk or a table or the wall, or between your hands really fast. You're going to feel heat generated. You're using mechanical work, moving your hand, to create friction. That friction is an irreversible process. You cannot take that heat that was generated by the friction process, return it to your body, and receive the calories from that. It's just, it's irreversible. It's not physically reversible. You cannot, now there are ways to take that heat and use it for other purposes, maybe to cook your food and replenish the calories that way, but that requires external devices to make it happen, so it's non-reversible. If a process is perfectly reversible, and the next question is related to this, very good, then hey, it's a perfect process. It doesn't happen in real life, never happened. We can try and get close to that. Well, cycles occur where you start at one process and you continue, and you series of processes that go back to the beginning again. Cooling, heating, heat exchangers, heat engines and refrigeration cycles are cycles. If they're all reversible, they're Carnot cycles. Peltier module is similar, is a type of cycle. And what we learn from reversible cycles is that the larger the temperature difference between the min and max temperature, so if it's a heat engine, the temperature of the combustion chamber, like the gasoline engine, and atmospheric temperature, the bigger that temperature is, the greater potential for higher efficiency we have. Doesn't mean we're going to get there, but it means we have a higher potential for that. If you've got a low temperature difference already, you're already looking at a very, very low maximum theoretical efficiency, which comes from Carnot cycles, which again, we don't need to get into that details on that. Carnot cycle is completely imaginary, would never happen in real life. We can't make that happen. We can get close to that, but not there. Well, Peltier cooler modules also has very low temperature differences. Just like Stirling engines can operate with very, very low temperature differences, which means they have low efficiencies. There's more to it than that, but that's already a big part of it right there. The lower the temperature difference on either side of the cycle, we call those the reservoir temperatures, hot and cold side. the less potential for efficiency you have, and your temp max efficiency is going to be dropped. Carnot engine, we cannot make a Carnot engine because the Carnot engine is composed of 4 reversible processes. We have isothermal heat addition, isentropic expansion, isothermal heat rejection, and isentropic compression. Isentropic processes are, in thermodynamics, are, well, not all reversible, not all isentropic processes are reversible, but all reversible processes are isentropic. You know, that's a question you might see on the PE exam one day if you take it. But the point is, we cannot create that. A Carnot cycle is 4 internally reversible processes, impossible to create exactly, but we can try and get close to that. So, for example, a steam power plant, well, or a gas turbine you might use. The maximum theoretical efficiency, according to Carnot, is maybe 70, 80% usually. We might be running around 30 or 40% in real life. It's much lower than that. But you know you can't get above 70 or 80%, and that comes from the second law of thermodynamics, the Kelvin-Planck statement. Second law, first law of thermodynamics is all about energy conservation. Second law is the temperature energy flows and moves, and has to do with the efficiency of cycles. Clausius statement and Kelvin-Planck statement. There's more mathematically to it, but the basic statement of that leads into the fact that you can only be so efficient. And that's Thermo 1 stuff you take as an engineer. How do you know if engineering is really the thing for you and not physics, comp-sci, or something else? That's another good question. And I don't have a good answer for that, honestly. I think that if you want to get into, if you're not so much into the application of things, and you're not so much, and you really love the math, and you are a mathhead, and you want to get into the fundamentals, how things really work down at either the particle level, the microscopic quantum level, or at the huge scale astrophysics level, you're looking at physics. There's obviously some middle ground in there as well. But engineers really, I mean, we aren't really engineering things at the quantum level yet. I mean, we're working at quantum level, but still all physics, and we aren't really doing things at the astro level other than spaceships. So I mean, there's obviously in between, but I think physics, my physics buddies that I know, they're all heavy into math. Also, good luck getting, and I don't mean this in a snarky negative way, but it's very hard to get a physics job without a job in physics without a graduate degree. If you're looking to just get a 4-year undergraduate degree, you can find a lot of work very easily with a 4-year bachelor degree of engineering. It's just that there's not a lot of physics jobs at that level. Physics is going to be graduate level, graduate school work, research. So if that's your jam, that's might help. Computer science, if you like coding and programming, computer science, great. Cybersecurity is great. But a lot of engineering work at the graduate level, especially, is programming and coding. I'm a self-taught coder because I had to do that in graduate school. You don't do a lot of it at the undergraduate level. Is a boiler a closed system? Another good question. If you have the cap on the top, like a pot, it's a closed system. But once mass leaves it, it's open. A boiler in a steam power plant is open because you've got fresh water coming in from the pump, you boil it, and it comes out into the turbine as vapor. If you got a pressure cooker on the stove, it is an open system because you have that little stopcock or popcock, I forget to call it. It's a weird name. It's just on the top, little weight that maintains the pressure, but steam comes out of it so it doesn't over pressurize and blow up. So anytime you allow matter to leave a system, it is open. So a boiler might be, a pressure cooker might be closed for a little bit while that little weight on the top keeps all the water and steam in there. But once it reaches the pressure that it's designed for, it pushes the little weight up and steam comes out and it's no longer a closed system. And we got 2 minutes. And it is a hard 2 minutes because this session goes into the next one shortly after, so they have to close it out. So maybe we have time for one more question. These are great questions, and all these questions here are basically thermodynamics part 1. Whether you're MET or mechanical engineering graduate, you're going to study it. Civil engineers get a bit of thermo, electrical engineers get a bit of thermo, but mechanical is a lot. Yes, zeroth law of thermodynamics is the most basic law of thermodynamics. It's used usually at the graduate level when you are trying to do thermodynamic proofs. In geometry, you do a lot of proofs. Graduate level thermo, you do a lot of proofs. As an applied engineer, it's so simple, it doesn't even matter. What it basically means is, say you've got these 3 objects. I got a knife, I got a remote, and I got a chapstick thing. If this chapstick thing is the same temperature as this knife, and this knife is the same temperature as this remote, then this remote and this chapstick thing also must be the same temperature. That's the zeroth law. Basically means, so if these 2 things are the same temperature and these 2 things are the same temperature, then the other 2 things have to be the same temperature as well. It's as simple as that. And that's where it's used in thermodynamic proofs. Like, you know, shortest distance between 2 points is a straight line. That's the zeroth law of thermodynamics. But then there's first, second, and third laws. So what makes thermodynamics wet? It's categorized in that because you're dealing with steam, you're dealing with phase changes, you're dealing with, it's technically called that because really applied thermodynamics is a lot more than just energy. It's applying it because we're saying, how do you take energy in one form, convert it to something more useful, which is done through heat engines and power cycles and vapor compression cycles, which all deal with fluids. So it's a lot of fluids involved. And we have about 1 second to go. I hope you all got something out of that. Looks like we are done. Feel free to email me other questions. I'm happy to answer.